Okay, so at this point you've had some experience balancing equations, but we want to give some specific strategies for solving some more difficult equations. So to review why we even balance equations, it's because of the law of conservation of mass, or law of conservation of atoms, which means that there must be the same number of each type of atom before and after the reaction, because no atoms or no matter can be created or destroyed. And to do that, we're going to use something called coefficients. And coefficients are just numbers that go in front of each substance to indicate how many of that substance are present. Okay, so let's try some examples, and we're going to be using something called the tally method to help us solve these equations. So our first step when we have our unbalanced equation is to write out each participating substance, so in this case aluminum and sulfur, beneath the arrow of our reaction. Now we're going to count and make tallies for the number of each substance on each side of the reaction. So on the left side of the equation first, we have one aluminum atom and one sulfur atom. On the right side, we have 2 aluminums and 3 sulfurs. Now, the point of the tally method is to help us visualize where we are balanced and where we are unbalanced. So both of our participating atoms right now are unbalanced, and we can see that we need to double the number of aluminum atoms on the left side of our equation. Once we do that, we will change the total number of aluminum atoms on the left side, and we can now see that our aluminum is balanced. Our sulfur needs to be tripled in order to make that balanced, and we don't have to do anything to the right side of the equation. Let's try another one. So with lithium and oxygen, we have 1 lithium and 2 oxygen on the left side, 2 lithium and 1 oxygen on the right side. So our first step to fix our lithium is to place a 2 in front of lithium on the left side of the equation. That balances lithium. Now for oxygen, we're going to have to put a 2 on the right side of our equation. However, this 2 affects both lithium and oxygen. So now our lithium is no longer balanced, which means we're going to have to erase our original 2 and write a 4 instead. Let's do a little more challenging one. And note here that we have some polyatomic ions like sulfate involved. We are not going to separate these polyatomic ions. So sulfate and phosphate both contain oxygen. Instead of trying to tally all of the oxygen total in the equation, we are simply going to tally sulfate and phosphate. So counting up on the left side of the equation, we have 2 iron, 3 sulfate, 3 sodium, and 1 phosphate. Counting on the right side of the equation, we have 1 iron, 1 sulfate, 2 sodium, and 1 phosphate. So the very first thing we're going to do, working from top to bottom, is remedy the discrepancy in our iron. However, we can't forget that this 2 also affects phosphate. Looking at sulfate now, we are going to place a 3 in front of our sodium sulfate on the right side of the equation. That balances our sulfate and also affects sodium. Moving down to sodium now, we can balance this 3 with this 6 by multiplying by 2. This is also going to fix phosphate. Now that each of our substances match, we are balanced. Okay, now it's time to put it all together. Let's go from a word equation to a formula equation and then balance it. So I want you to pause the video right here and try to write the formula equation for this reaction. Okay, so magnesium chlorate. Magnesium is going to have a 2 charge, a positive 2 charge. Chlorate's going to have a -1 charge. We crisscross those to get MgClO3, 2. Now magnesium chloride. Magnesium has a positive 2 charge. Chlorine has a -1 charge. We end up with MgCl2. Oxygen is just an element, but it is one of our diatomic elements, so we have O2. Now pause the video again and try and balance this equation. Okay, so we are going to demonstrate using the tally method by writing out each component of our reaction beneath our reaction arrow. And let's count. On the left side, we have 1 magnesium, we have 2 chlorine atoms, and 6 oxygen atoms. On the right side, we have 1 magnesium, 2 chlorine, and 2 oxygen. Okay, so again, one of the really nice things about the tally method is it shows us really quickly and easily that magnesium is already balanced and chlorine is already balanced. So all we have left to worry about is oxygen. We have 6 oxygen atoms on the left side of the equation and 2 on the right side. So we are going to ask ourselves, what times 2 equals 6? Of course, that number is 3. And now oxygen is balanced as well. One more time, go ahead and pause the video, try and write the formula equation for this reaction. Okay, so looking at this, we have potassium carbonate, which is going to be K2CO3, chromium 3 nitrate. Remember that this Roman numeral 3 right here tells us the ionization state of chromium. So we have CrNO3, 3, potassium nitrate, which is just KNO3, and chromium 3 carbonate, which is going to give us Cr2CO3, 3. One more time, pause the video, try and balance this equation. Okay, so let's count up each atom on the left side. We have 2 potassium atoms, 1 carbonate, 1 chromium, and 3 nitrate. On the right side, we have 1 potassium, 3 carbonate, 2 chromium, and 1 nitrate. So to start, we're going to look at potassium. We're going to go ahead and put a 2 on the right side of the equation. That fixes potassium, and it also changes nitrate. So next up, we are going to fix carbonate by putting a 3 on the left side of the equation. But of course, that also affects potassium. We now have 6 total potassium on the left side of the equation. Looking at chromium, we have 2 on the right side. We're going to put a 2 on the left side. And that also changes nitrate on that side. So now we're going to look back and say, okay, carbonate and chromium are both balanced, but we have a problem with potassium and nitrate. So we're actually going to change that 2 that we originally wrote next to potassium nitrate into a 6, and now we're balanced. So moving on now, we are going to talk about the 5 main types of chemical reactions. And we are going to start with synthesis and decomposition, and we're going to talk about how you can predict the products for those reactions. So the 5 types are synthesis, decomposition, single replacement, double replacement, and combustion. Synthesis is defined as when 2 elements combine to form a compound. So that takes the general form of A plus B yields AB. We have 2 things coming together to make something bigger. So some examples: sodium plus chlorine yielding sodium chloride. Magnesium plus phosphorus yielding magnesium phosphide. And sulfur plus aluminum yielding aluminum sulfide. These are all named the same way we named compounds last unit, with the nonmetal dropping its own original ending and getting an IDE ending. For decomposition, it's kind of the opposite of synthesis. We have something larger breaking down into smaller pieces. So that looks something like AB yields A plus B. It's breaking apart. And some examples: potassium nitride breaking down into potassium and nitrogen. And something to note here, we go back to the nonmetal's original ending. So instead of nitride, it's going back to nitrogen. We do have a few special decompositions. So the first one is when we have a metal chlorate, and it's going to break down into a metal chloride and oxygen. So for example, barium chlorate breaks down into barium chloride and oxygen. This chloride plus oxygen will always be a part of the product for this special kind of decomposition. And then whatever the metal is just moves on over. Another type of special decomposition is a metal carbonate, which yields a metal oxide plus carbon dioxide. For example, potassium carbonate breaks down into potassium oxide and carbon dioxide. Just like last time, this yellow part, the oxide plus carbon dioxide, is always going to be a part of the product. The third kind of special decomposition is a metal hydroxide breaking down into a metal oxide plus water. So for example, tin 4 hydroxide yields tin 4 oxide plus water. Okay, we have to remember to carry over the Roman numeral because tin is still part of a compound, and just like before, this oxide plus water will always be a part of the product. Okay, now let's talk about single replacement reactions. In a single replacement reaction, an element and a compound react to form a different element and compound. So for example, it's going to look something like A plus BC yields AC plus B. We're kind of switching out. So something important to note is these reactions don't automatically always occur. They depend on the activity of the metal. And metals will always replace metals, nonmetals always replace nonmetals. So, as a rule, a metal in a compound is only replaced by a more active metal. We have to make sure that lithium is more active than zinc, so we have to use our activity series. Now here is the general activity series of metals. You will find this inside your periodic table reference chart that you have access to in class. And we can see that lithium is in fact more active than zinc. So we end up with zinc plus lithium acetate. Let's try another one. If we have copper plus aluminum sulfate, we are going to check the activity series. Aluminum is higher on the activity series than copper, so we have no reaction. Okay, let's try some more examples. Lead 2 carbonate plus barium. Check the activity series. Barium is higher than lead. We end up with barium carbonate plus lead. Now, hydrogen in water will be replaced by a more active metal. So this is a pretty common reaction that we see. So sodium plus water, we can rewrite water as hydrogen hydroxide, HOH. Sodium is in fact more reactive than hydrogen. So we end up with sodium hydroxide plus hydrogen. Same thing with acids. A hydrogen in an acid will be replaced by a more active metal. So if we have calcium plus phosphoric acid, which we can rewrite as hydrogen phosphate, this is the ionic name for phosphoric acid. So calcium is in fact more reactive than hydrogen. We end up with calcium phosphate plus hydrogen. And lastly, a nonmetal in a compound is replaced by a more active nonmetal. So fluorine plus magnesium iodide. The reactivity series of nonmetals is much shorter and simpler. Fluorine is in fact above iodine. So we end up with magnesium fluoride plus iodine. Make sure to keep an eye on those endings. Okay. Next up, the last two types of chemical reactions, double replacement and combustion reactions. So a double replacement reaction is when two compounds react to form two different compounds. So that looks something like AB plus CD yields AD plus CB. An example of this is copper 1 sulfate plus beryllium oxalate. We do not need to use the activity series for these reactions because one of those metals is obviously going to be more active than the other, so the reaction will happen. We end up with copper 1 oxalate and beryllium sulfate. So a special type of double replacement reaction is called a neutralization reaction. So this is a reaction between an acid and a base, and we will have much more in-depth conversations about acids and bases later. Okay, so an example of a neutralization reaction would be aluminum hydroxide plus nitric acid. Now, it's going to help, just like with single replacements, to rewrite acids in their ionic form, so hydrogen nitrate, and we end up with aluminum nitrate and water. In a neutralization reaction, water will always be one of the products. Okay, now talking about combustion. The simplest definition of combustion is just a reaction with oxygen. For example, if your reactant contains carbon, the product will be carbon dioxide. If it contains hydrogen, the product will be water. If it contains sulfur, the product will be sulfite. And if it contains nitrogen, the product will be N2. So if we have CH4 methane reacting with oxygen, we know that we will have carbon dioxide and water. Now pause the video for a second and try to balance this equation. Okay, so let's count from the left side. We have 1 carbon, 4 hydrogens, and 2 oxygens on the right side, we have 1 carbon, 2 hydrogens, and 3 oxygens. So the first thing we're going to do is fix hydrogen, which will also help out with oxygen. We can now put a 2 on the left side next to our O2, and we can see that everything is balanced. So as a general rule with combustion reactions, we always want to balance the O2 last. One more example, go ahead and pause the video here, try and balance this reaction. Counting, we have 3 hydrogens, 1 nitrogen, and 2 oxygens on the left side, 2 hydrogens, 2 nitrogens, and 1 oxygen on the right side. So again, we're going to save O2 for last. We will start with hydrogen. We are going to make 6 on the right side, which also changes our number of oxygen. We'll then make 6 hydrogen on the left side, which also changes our number of nitrogen. And then we've kind of hit a wall, right? We have an uneven number of oxygen, and because we have a 2 subscript here, we can't make an odd number. So there are a couple of ways to do this. One way is to just go ahead and double all of the current coefficients. So this would become 4, this would become 2, this would become 6, this would become 2, and then we continue trying to balance. Or we can put the ideal coefficients in decimal form and then double. So what times 2 would equal 3? 1.5. And then we are going to double everything. And we can see everything is now balanced.